Good afternoon. I'm April Strom, and I have the distinct honor of introducing our next MAA invited speaker, Scott Adamson. I have worked alongside Scott for over 15 years, and we frequently collaborate on projects that are vital to the development of students and teachers in the field of mathematics education. Let's just say that once you've been hanging around with Scott for a while, there are a lot of laughs along the way. Scott's one of these people who tells the corniest of jokes, so you do have to have one of those jokes told. Just ask him about the Ollie and Sven jokes. They're super famous by Scott. Scott has a deep passion for the teaching of mathematics and the spreading of joy of mathematics broadly throughout the community, but his forte is that he connects with students on a human level. He has been teaching mathematics for over 30 years, and when asked what he teaches, he responds with, "I teach students." As Scott says so eloquently, certainly we teach our students the beauty, wonder, and utility of mathematics, but we must realize that the positive relationships that we build with our students are the most important. In addition, Scott is intensely engaged in working with teachers at all levels throughout the state of Arizona and across the nation with respect to developing their mathematical knowledge for teaching and understanding of the mathematical practices. On a personal level, I can say with absolute certainty that Scott is one of the most amazingly talented, kind, and passionate humans I've had the opportunity to work with. I count myself quite lucky and blessed to have crossed career paths with Scott, as my own philosophy about the teaching and learning of mathematics has been largely shaped by the ideas he promotes. So without further ado, it is an honor to call to the podium my best frolic, Scott Adamson.
Thank you. Thank you, April. Hi, everybody. So good to be here and to share with you. You might be wondering, what in the world are we going to be talking about if there's mazes, riddles, zombies, and unicorns? You want to find out? Well, we're mathematicians, right? So let's first start by understanding the problem. That's what I want to talk about here tonight first, is I want to understand a problem as I perceive it. As April said, I work with teachers across Arizona, and I see a problem, and I want to tell you about it. Then I want to share a plan. And then I'm just going to expect that you're going to take it from there and carry out the plan and look back. Here's the problem as I see it. Even this week, my classes started at my college this week. And so, of course, I'm not there. And so my students are doing some things and emailing me and a little introduction. And here's what I'm hearing. I'm not good at math. I'm just not a math person. Nobody needs math anyway. And they have no idea that when I get back next week, this is the goal. And I want us all to think about this here today. How can we create a more joyful mathematical learning experience where the beauty and awe of mathematics can be shared in and engaged in by our students? You've all seen the international rankings, though. We don't do so well. Do you see the United States up there? In case you can't see it, it's right there. Now, that's a whole nother talk. I'm not going to get into these international rankings, but just know that I perceive it as a problem that we rank low. Recently, I had a high school student come to me and say, "Hey, can you help me with my calculus homework?" I'm like, "Sure. Show me what you got." And here's what he had. Can you see it? He has to memorize. You know what he has to memorize? That. He didn't understand. He's like, "What is this stuff I'm memorizing? I don't even know what it means." And then his homework was this. Do these limits, no calculator. Now, I'm not saying that there's not a place and a time for no calculator. What I'm saying is this student did not understand what he was doing and why a calculator would have helped or not helped or anything. We have a problem. In the era of Google, we don't need people who memorize. We need people who can think. And memorizing those limit formulas, we're not helping this student to think. Some of my work I do with teachers, I work K through 12, and you'll recognize this as a pretty common 6th to 8th grade middle school topic. We're studying integers, and the approach was this. All right, kids, when you have an integer operation situation, here's what you do. All right, if they're on the same team, you add. If they're on different teams, you subtract. If the bigger team, look for the bigger team, they win. And the sign in front of the number determines the team. Don't forget, minus minus equals plus plus. And addition is commutative, but subtraction is not. Here's how it looks. 5 minus 8, here's what you do. All right, first of all, make a little T-chart. Get your teams ready. We have a positive team, you have a negative team. Oh, never mind, is that a minus or a negative? No, it doesn't matter, just look at the sign in front of the number. We'll go on the minus team, the negative team. Different teams, what do? So you're supposed to say subtract. Subtract, yes. And you subtract and you put the answer on the side of the bigger team. And so the answer here is -3. All right, well, what about this? What if you have -7 minus -2? Oh, don't forget, minus minus equals? Yeah. Now play the game. Put your teams together. You have a team over there. You have a team over there. Different teams, you should put the team on the side of the bigger number. They win, and so the answer, of course, is -5. Now, here's the problem. I don't think we're doing math. We're playing a game. What's the mathematics behind all this? And then here's what we see. Kids learn these rules, and they apply them when they don't need to. Now, kids in 6th, 7th, and 8th grade, I'm not saying all kids, but this is a pretty common observation. 7 minus 2. They learn this in 2nd grade, but now they have to play the game. Oh, first I have to make a chart. I have a positive and I have a negative. I put the positive on the positive team, I put the negative on the negative team. Different signs, you should? Put the sign on the positive. Oh, the answer is 5. What in the world? Why are we playing this game now? But we see it all the time. And I will argue that in this case, this problem is the same as 7 minus 2. If you have 7 negatives and you take away 2 negatives, how many negatives are left? Why are we playing this game? This problem is conceptually, cognitively speaking, equivalent to just 7 minus 2 equals 5. But they're just learning rules, and that's a problem. And then now we have to practice the rules. They get good at it. So here's what we do. We give them a maze. Now this is a recent one from Christmas time. And so the maze is this. You start up there in the upper left. You do the operation, and you follow the path to the right answer, which gives you another operation, which follows a path, follows a path, follows a path. And when you complete the maze, you win. What about this? We teach students around late elementary, early middle school, we talk about the average, and we tell them how to do it. But we don't tell them what it means. Suppose you had 6 ages, 23, 19, 15, 22, 20, and 53. That was me. What is the average age of this collection of people, and what does the average mean? Well, kids have no problem. Bam, do it. Add up the numbers. Divide by 6. You get 25.3. And I say to the kid, what does that 25.3 mean? And they say, it means I added up all the numbers and I divided by 6, and I got 25.3. That's not what it means. That's what you did. That's the computation. But what in the world does that number mean? How about this? Here's those ages, mine at the bottom. I'm going to take some of my extra years, and I'm going to give them to that guy up there. And I'm going to take some more of my extra years. I'm going to give them to that guy right there. I'm going to give some more up there. I'm going to give some more there. I'm going to give some more there. I still got 2 more extra years, 6 of us. So I'm going to give 2 of my years to 6 people. That's a third each. So on average, if all of our ages were the same, if we equally distribute our ages, we're all 25 and a third years old. But students don't learn what this average means. They just learn how to do it. And so then to get them to practice it, we give them a worksheet. And the worksheet looks like this. You have a bunch of problems on there. I hope you can kind of see the idea here. You have a whole bunch of problems. Each problem produces an answer. Each answer aligns with a letter, and you put the letter with the associated answer down at the bottom of the page to answer this riddle. Anybody know? Why was the girl staring at her juice box? Because it said to concentrate. Are we doing math? Or are we trying to do a riddle? Then we have this situation, the magic square, everybody. Let me introduce you to the magic square. Suppose a scale on a map shows that 3 inches, 52 miles. On the map, the distance from LA to Portland is 55.5 inches. What is the actual distance from LA to Portland? All right, kids, here's what you do. You make a magic square. You put the numbers in the magic square. The actual measurement was 3 inches. The actual distance is 52 miles. The model, 55.5 inches, what was the actual distance from LA to Portland? And then you make a butterfly. And you cross multiply, and you solve for x, you get 962 miles. Awesome. So I was in a classroom, kids were working on this problem. They're expected to fill in the magic square, do the butterfly method, get an answer, yay. This one kid was like, I don't understand what number goes in the magic square, and I just started asking him questions. And this kid starts answering my questions, and he says, well, the first thing I'd want to know is, how many 3 inches are in 55.5 inches? That's a great thing to ask, isn't it? And he finds out there's 18.5 groups of 3 in 55.5. Awesome. Then he says, for each of those groups of 3 is 55.5 inches on that map. And so the actual distance was 52 miles. So I think I need to multiply to figure out the distance. He kind of reasoned his way through it. And what was awesome was he did the butterfly method. If you look at the cross multiplication here, he had to do 55.5 divided by 3. He had to multiply that by 52. He did the method, but with a lot more meaning. But the expectation is, do the butterfly method and just produce a right answer. And then practice. How do you practice? One of the worksheets they do is to take this picture of a unicorn and scale it up using some proportional reasoning. So there's the unicorns. Now here's my recollection. I started teaching 32 years ago, and I can remember this vividly, not with a happy thought, but I can remember teaching my students to do this. And I would tell them, all right, class, remember. And can't you just hear your students right now saying, wait a minute, is it x2 minus x1? Is it y squared? Is it x, oh, remember the formula. And then don't forget, y equals mx plus b. And then let's go to work. Here's what you do. You put that number there, you put that number there, 5 minus 3, negative 1. Hey, can you go 3 minus 5 instead of 5 minus? Yes, as long as you do negative 1 minus 2 instead of 2 minus negative 1. Yeah, you just got to keep it all in the order they get the slope. Step 2, don't forget, plug this number in. There's your m. Step 3, pick a point. Which point should you pick? Doesn't matter, pick a point. Maybe pick one that's easier, but pick a point, plug it in, solve for b. All right, awesome. Step 4, you get your answer. Except in my class, most students wouldn't use fractions because they're scared of fractions, so they would put it in decimal form. And then, of course, you're not done yet, because what do you have to do when you're done? Circle your answer. Except I boxed it, I know. So I do this now, and I don't teach this way anymore, but students will eventually kind of see through my stuff, and they'll go, hey, wait a minute. Isn't that y equals mx plus b thing? I understand it that way. And my claim is they don't really understand. When my students say, I understand it that way, what they really mean is, I remember doing that before. That's not understanding. So I have a question. If the learning goal is for students to write a linear function given 2 points, instead of my little, hey, step 1, step 2, step 3, remember this, plug this there, how about this? All right, kids, first click that plus sign. Choose the table. Type in the numbers in the right order. Put that number there, put that number there, put that number there, put that number there. All right, then click down here and type this in. Type Y1, and then go find that little tilde button, and then type AX. Oh, no, don't use A. You better use M. It'll understand it better. MX1 plus B, and boom! You got the same answer. So my question is, I just have something to ponder. I don't know if there's an answer to this question, but I want you to ponder it. Is there a difference, cognitively speaking, in teaching the student to follow the steps in the paper pencil case compared to following the steps in the Desmos case? It might be that in either case, they're just following steps and getting an answer. Pat Thompson at Arizona State University says this: any company that might hire you already has a $350 computer program or handheld app, or even worse, free access to Wolfram Alpha that can solve equations, simplify, differentiate, integrate functions faster and more accurately than you ever will. But then here's what we do. We give students these little worksheets. Practice this skill of getting linear functions, and we have them graph and we have them kill zombies. Because that'll be fun.
Yeah, but the zombies are all right, Dad.
Thank you. Are we teaching mathematics or, I don't know if you've read The Mathematician's Lament by Paul Lockhart. He says, in fact, if I had to design a mechanism for the express purpose of destroying a child's natural curiosity and love of pattern making, I couldn't possibly do as good a job as is currently being done. I simply wouldn't have the imagination to come up with the kind of senseless, soul-crushing ideas that constitute contemporary mathematics education. This is a long quote, but bear with me here. By concentrating on what and leaving out the why, mathematics is reduced to an empty shell. The art is not in the truth, but in the explanation, the argument. It's the argument itself which gives the truth its context and determines what is really being said and meant. Mathematics is the art of explanation. If you deny students the opportunity to engage in this activity, to pose their own problems, make their own conjectures and discoveries, to be wrong, to be creatively frustrated, to have inspiration, to cobble together their own explanations and proofs, you deny them mathematics itself. So Paul says, no, I'm not complaining about the presence of facts and formulas in our mathematics classes. I'm complaining about the lack of mathematics in our mathematics classes. In an institution I worked with, this was some learning competencies for an algebra course. Look at the verbs: perform operations, evaluate, simplify, perform, write, solve. If this is the goal, is to just make this happen, we could make this happen by giving students one of these. Oh, they already have one. We could have students access one of these for free. And then all of those learning competencies could be accomplished with that device. So what's my point? Now, this is just me thinking. You guys, I'm going to give you a little insight into my brain. Now, this is a little scary for me to share, but this is just my brain leaving a school at the end of a day or thinking in the middle of the night. You all know how it is. You have thoughts in the middle of the night. And I'm just sharing with you some of these thoughts. So they might sound a little extreme, but they're just thoughts I had. So I had this thought: mazes, riddles, zombies, unicorns. What we're really saying possibly is this: math is so senseless to our students. You borrow, you carry, you do this keep, change, flip thing. Butterflies and magic squares. Math is so senseless that in order to keep them engaged, we have to mask all that procedural mathematics with games, mazes, riddles. Perhaps, unwittingly, we're telling students, we know that this is almost unbearable, so we will make it as painless as we can by using unicorns and zombies. In high school mathematics, students have become trained to believe that math just cannot be made sense of. In one particular case, I witnessed a student raise their hand and ask a teacher, why do we do this thing when we complete the square? You take half of this number and square it and do all this stuff. The student says, why do we do that? And the answer was, that's just how math works. And I thought, but what followed even hurt me more. The student said, oh, okay. That has become an acceptable response when a student actually asked a great question and wanted to dig into the mathematics. The response was, that's just how it is. Oh, okay. And then college math, hang with me here. I teach at the college level. This hurts a little bit. This is a thought. It's a thought I had. I'm sharing. You can throw eggs at me later. In college, perhaps, the math is so complex and hard to make sense of that we have made the learning experience even more mind-numbing for the typical student. Here's what we say: come to class, watch me copy the notes from my notebook to the chalkboard. You copy the notes from the chalkboard to your notebooks. This is doing mathematics together? Do we even need students to do this kind of teaching? So now what? That's the problem as I see it, you guys. I know there's some extreme cases here, my weird thoughts, I know, but this is the problem as I see it, and I want to talk about how we might change what we do at all levels. This is from a researcher named Dylan William. He talks about 3 things. There's a lot of good things we can do, but some things that we can do are really too expensive in terms of time, money, resources. There's 3 things that we can do that have great impact that are not expensive. Get a rich curriculum. Create a learning environment for our teachers to work together collaboratively, and focus on formative assessment. And for the rest of this talk, I want to focus on this 3rd thing, this formative assessment idea. What is formative assessment? We use the general term assessment to refer to all activities undertaken by teachers and their students in assessing themselves that provide information to be used as feedback to modify teaching and learning. This assessment becomes formative when the evidence is actually used to adapt the teaching to meet the students' needs. Are we listening to our students? Are we taking in evidence of our student thinking and then doing something about it? That's formative assessment. It's the process used by teachers and students to recognize and respond to student learning in order to enhance that learning, and it happens during the learning. This is the key thing I'm going to share with you today, is when we are engaged in a learning environment such that my teaching is changing minute by minute, moment by moment, as I hear and see and reflect on what my students are doing. Formative assessment. It's assessment carried out during the instructional process for the purpose of improving teaching or learning. Now, teaching or learning. Another researcher says teaching takes place in time, learning takes place over time. I want you to imagine this, the teaching that's happening in the classroom, very important. The learning is going to happen over time. Formative assessment, it's the greatest impact on learning is the daily lived experiences of students in classrooms that is determined much more by how teachers teach than by what they teach. How they teach rather than what they teach. Now, the what's important. Hey, I teach calculus, I teach this class, I teach this class. The what is important. But the how is really going to impact my student learning. So, here's a how. Here's an idea for a how. I'm stealing it from Peter Liljedahl. His research is called Building a Thinking Classroom. And among about 14 elements, I'm going to focus on the top 3 elements. The top 3 elements is the use of visibly random groups, in my case, mostly pairs, the use of good problems, and the use of vertical non-permanent surfaces. What? Vertical, non-permanent surfaces. Are you ready for this? Yeah, focus on thinking. What a teacher says in the classroom is not unimportant, but what the students are thinking is 1,000 times more important. George Polya. So what does it look like? First of all, a good problem. We live in a day and age now, I claim, that we can access good problems from our textbooks, certainly, maybe with some adaptation, but we have resources all over the internet. Peter Liljedahl himself, Dan Meyer's 3-act task, if you're not aware, check them out. Open Middle, Robert Kaplinsky, the Illustrative Math Project, the Arizona Mathematics Partnership, Good Questions Project, Math or Mars, Graham Fletchy, as he goes by, all the NCTM stuff. There are good problems everywhere. I want to describe one for you, my opinion, a good problem that I used recently in a Calculus 1 class. Students are given this. Now, my students at this point have never used the fundamental theorem of calculus. At this moment in their learning, they have not done it yet. On this day, I come into class, I hand out this problem, here it is. They're given a velocity time graph. And it's about a car driving east and west on a highway. Let's see if I got to remember this. Positive values indicate eastward displacement, negative values indicate westward displacement, and I just send them up to the boards. And I say, hey, work on filling out this chart. Now, the first thing that they do, if you can imagine this, do you see that time equals 0, S of t is 0? They ignore that. They jump to time equals 10 seconds. Hey, everybody, look at the graph. At time equals 10 seconds, the velocity of the car is 60 feet per second. Are you seeing it with me? They put 60 in that box right there. And then they put 20 in the next box, and then 0 in the next box, and then they put negative 60 in the next box, etc. And I stand there and I look around the room because they're all up at the boards, and I see what's happening. And I assess in that moment, formative assessment. That's what they're thinking. Just literally read the numbers off the graph. And I just stop, everybody. Stop for a moment. What are you doing? What is this? We have a little quick conversation. And we set things straight. All right, back to work. And they go back to work. This is what I mean, just a quick example of formative assessment. I see my students' work, I see my students thinking, and I can adjust and adapt in the moment and make a pedagogical decision. So, I did have a zoom in. Sorry, I had a zoom in on it even. So here's how it goes. Students walk into my class. First thing I do is I push a button on this app called Class Dojo, and boom, they're put into random groups. Now, there's really important reasons I don't have time for today in terms of why random groups. But it's important that at the end of my class, my students have probably worked with everybody at least once. What happens there is the kids don't have a sense of, oh, I'm not good at math, so I'm going to shy to the background. Because when we place kids purposefully, maybe we place a high and a middle and a low together, I tell you, the low kids know they're the low kid, and they know who the high kid is, and they shrink to the background and let the high kid lead. When I make the groups visibly random, they don't know who they're being paired with, and the discussion, the collaboration, the engagement just increases greatly. And after about a week of this, it becomes normal. Nobody complains. Students walk into my class, they just know, okay, push the button, let's see who I'm working with today. It takes about a week, maybe 2 weeks for that to happen. Then, vertical non-permanent surfaces. When we're done, we get them up to the boards. Now, this takes some work. We've been working at my institution to get whiteboards put around the walls. Sometimes we write on windows if we need to. But here's why. Let me tell you about this vertical non-permanent surface. This is from the work of Peter Liljedahl. And he's done this now, I don't know the numbers, but it's like he's repeated this many times, and here's the finding. So, students are asked to work on vertical non-permanent, horizontal non-permanent. Maybe some of you have the smaller whiteboards that you can plop down on a desk and some kids can collaborate around that horizontal surface. Vertical permanent would be something like a chart paper, big sticky notepad you put up on the wall and you say, hey, go write your thinking up on that wall over there. Horizontal permanent would be the situation where the same butcher paper or chart paper is used on a desk and then students writing in their notebook. And he measured with a group of observers several things. Time to task, first notation. Not quite the same. Time to task might be just, how long does it take before they engage? First notation, how long does it take them to just start with something? How many of you have been in that classroom situation where you give the student something to do and within a minute, hands are up, I don't get it. This is an attempt to get that to go away and have students just try something. So time to task, first notation, you can see across how those things go. Especially, will you all look at the first notation row? First notation, 20.3 seconds, 23.5 seconds, 2.4 minutes, 2 minutes. But hey, my notebook, I'll put it in my notebook. You're probably not going to see it anyway. So 18.2 seconds. But here's the idea. Why does it take students so long to get that first notation on a permanent surface? They're scared to write something. What if it's wrong? But when it's on a non-permanent surface, if they put it up there and it's wrong, you can just wipe it away. So that fear of engagement goes away. And then he measured on a scale from 0 to 3, 0 being bad, 3 being good. You have to read the paper to see how they measured all that. But look at the columns about the amount of discussion, the eagerness to engage, the amount of participation, the persistence, the mobility. And what we see there is the non-permanent surfaces win out. So using non-permanent surfaces is a powerful way to engage students in doing meaningful mathematics with a good problem with a randomly assigned partner. But then even among those two, vertical or horizontal, you can see that the vertical non-permanent wins out. And so it's become a movement. Vertical non-permanent surfaces. I know, just say whiteboard. Well, it might be a whiteboard, it might be a chalkboard, it might be a window. But the idea is students engaged in doing mathematics together at a non-permanent surface. If you hashtag or you on Twitter, you can look and see people are talking about this. VNPS, vertical non-permanent surface. So here's a look inside my classroom. This was a Calculus 3 class. You see the kids standing on the vertical surfaces. At that stage, we were lacking a wall of whiteboards. So you see the two kids in the back. So all the kids on the vertical whiteboards all aced the class. The two in the back got C's. You know, the horizontal, it was horizontal. I'm just kidding. Here's another scene. Now we have whiteboards on all three of the walls. The wall behind this picture is windows. Sometimes we use that too. But what I want you to see here is what are the students doing while they're on these whiteboards. So this was a pre-service elementary education class. So these students are working on fraction operations, and I don't remember exactly the task, but I asked them to engage in thinking about operations with fractions, but to make sense of it. And so they're working on it. You can see visual representations. You can see them writing word problems to correspond to their operations. Lots of discussion going on. Now, in this case, they started in pairs. But what happens is the mobility issue that Lilladall talks about is this, knowledge mobility. So across the room, something's happening, and some of the students will say, hey, come over here and talk to us about that. And so the mobility of the knowledge, because students are engaged together, in this particular thing we had, about 3 groups got together to share their ideas. Here's 2 students engaged in one of those 3-act tasks from Dan Meyer, thinking about the mathematics, explaining to one another. And I just have a couple of quotes I'd like to share with you about what students say about this. Of course, now I talk to teachers about this, and I'm kind of excited about the idea of vertical non-permanent surfaces and having students engage. And so I asked my student, hey, what do you think of this? Madison said, back in her other math classes, they simply showed us how to do a problem on the board, and then we'd have to memorize it and copy. This year is the first math class that I've used a whiteboard and markers to show our work. Since doing so, I've learned more because I was able to work with a partner and look around the classroom at other people's work to get ideas. If I'd have started that in first grade, maybe I would have comprehended math a little bit better. Now, this is just Madison, a student of mine who says this, but what I want to highlight here is this idea of looking around the room at other people's work. This is a good thing. This is not an assessment that's going to be a summative assessment that's going to be a grade. This is a learning experience. This is students working together at the whiteboards. I'm typically running around the room, poking, asking questions, pushing, encouraging, sometimes challenging, sometimes working to produce more productive struggle for a group that needs it, sometimes supporting when a group is really struggling in a negative way. But this group, this girl says, I look around the room and I see what other people are doing, and that helps me to learn in an active kind of a way. This student, Trish, says, I wasn't able to build off the knowledge I should have learned because all I actually learned to do was copy notes down in a notebook. That's become a thing. I go to schools and it's, all right, class, it's notes time. And notes time is you just copy stuff off of the PowerPoint now, back in the day, back off the overhead projector. A student, Miles, says, I unfortunately was one of the students that primarily learned to imitate the teacher's solving methods, which naturally resulted in me struggling when we were assigned problems that didn't match the provided examples. Much of math throughout middle and high school felt like a cheat memorization game and a flood of countless number problems. I did not prompt Miles to say that. This is Miles thinking after his experiences with this vertical non-permanent surface kind of environment. And this is very interesting and intriguing to me because I have a goal in my classroom of helping students to solve problems. Not solve this problem, but perhaps solve any problem. So how do we as instructors get to a place where our student experiences are such that they can take the ideas that they're learning and apply them to this or to this or to this? Now, I have to admit, at least in the beginning, students will come to me and go, oh, I don't like this. I'm working on number 7, and I look back in the book, and I can't find an example like number 7. I looked at my notes. You didn't teach me how to do number 7. So we are trying to help them to see that your goal as a student is to understand ideas and learn how to better problem solve and apply them. I want to have you hear some voices. So, of course, as I go around and talk about this, I want you to hear not just from me, but from students. I just have a couple of short clips.
All right. I really enjoy doing classroom activities on the whiteboard because specifically in math, it gives me and other students the opportunity to attempt the problem instead of being afraid to be wrong. It's okay to attempt it and have your classmates correct you and help you and answer your questions. So I think that's the biggest benefit. It lets me attempt the problem and not be afraid of math.
Now you have to trust me here. I did not ask these students to say anything. In fact, it was very impromptu. I was going from this class to a workshop at my college with faculty from all across the college. And in a minute, I just said, hey, I would love to get some student voices. Could I have some volunteers? Tell me about this experience with vertical non-permanent surfaces. And he says what he says. And I love this idea when he gets corrected by other students. The learning that has to take place for another student to recognize what's happening and say, hey, I think there's an error there. We learn so much by making and correcting mistakes. Joe Bowler says we should have a classroom where mistakes are expected, respected, and inspected. And that's what he's talking about. We expect to make some mistakes as we learn. We respect that. Build this culture in the classroom of respect, and then the students help each other out to correct those mistakes. Here's another one.
Using the whiteboards lets us as like a group really like feel out the problems, like in math specifically, because we can like see them and then like go through and edit them, which is nice about being non-permanent vertical surfaces because they're not permanent. And I think it helps seeing how everyone else is learning, because you can like see on the board what they thought about, and then you can see like, oh, this is how I thought about it, that's how they thought about it, and you sort of like can implement whatever they learned in something that you're trying to like also learn.
Again, I did not script anything, but I love what he says. I like to see how other students are thinking about something. So sometimes I give them these problems without any previous instruction. Like I don't, hey, here's how you do it. Okay, now go to the boards and do it. I give them problems that they don't know how to do yet, really. They have some underpinning ideas that they can start working on things, and you'll have an idea here, an idea here, an idea here. And then my job, the way I see it, is to facilitate the discourse around that room. I'll have this group share, this group share, this group share, and we'll talk. And what happens is, this is Quinn, by the way. I love Quinn because he dresses the same way I dressed back in 1972. Quinn is awesome, and Quinn says, I love that, because Quinn will sometimes look over there and see Sally's work and say, I'm going to do it like Sally's doing it. That makes way more sense than what I'm doing. And that kind of mathematical engagement is now what we want. Here's one more. This is Quentin Green.
All right. I enjoy math, and math comes relatively easy for me, I feel, but one of my biggest issues in math is getting ahead of myself. I like to jump forward and just kind of come upon where I think the solution's going, but going up to the whiteboards with my classmates has made me dial that back and forced me to actually think about what I'm putting in front of somebody else's face right now. And it makes it to where I have these aha moments where I'm like, oh, that's why I jumped to that conclusion. Oh, that's how I get there. And it makes it so much easier for me to sort through my thoughts, because sometimes it's hard for me to articulate them to myself even. And it forces me to for somebody else. And it's helped a lot.
You've all been there. If you've been in a classroom for 2 seconds, hey, Quentin, how did you get to that result? I don't know. I don't know what I did. I just got there. And Quentin is realizing that when he does mathematics, he's not doing it just for himself. He's doing it for an audience of his peers, and perhaps me too. So when he's working, while he admits or he confesses that he's somewhat kind of good at math, or it's come easy for him over the years, he now has to slow himself down and think about, how am I going to explain what I'm doing here? And that thinking is just taking him to another deeper level of engaging in mathematical thought. I have one more.
Go. So the whiteboards have helped us a lot. One thing that I think could help even further is having smaller classes, and that way everyone has whiteboard space and a marker. That way we can all participate, and I think that has really helped the learning of this class, at least in this class.
I know you're all going to laugh. If you teach in a setting where you have 100 or 200 students, this is a class of 32. And he's saying, we should have smaller classes. Because in my class of 32, while we have whiteboards on 3 walls, it gets a little crowded at times on those vertical non-permanent surfaces. And so his desire is, could we have smaller classes so we have some more space to work? And could we have some more whiteboard markers? Because sometimes they just disappear. And so that becomes a struggle. But the idea here is this. This is a student who is coming to class engaged in what we hope is a good problem, working with different people all the time and hearing different voices, having to communicate his own thinking with others. And this is, he claims, helping him to learn mathematics and engage. So, what's my point? My point is this. Can we think about how can we create more joyful mathematical learning experiences where the beauty and awe of mathematics can be shared and be engaged in by our students? And so I'm going to end there. And April, we have time for some questions.
Thank you, Scott. Yes, we have about 8 minutes, 9 minutes or so for questions. So we have 3 mics, one in the center and one on either side. If you have a question, if you could please walk up to the mic and speak, in part for us to hear, but also in part for us to get on the video and hear as well. So are there any questions for Scott? Right. Looks like the mic is not working over here.
Okay. My classroom. Oh,
Hold on. I can hear.
So, for example, calculus 3. Pretty much all the time that I have is devoted to lecturing. It's when I have no extra time to give time to go. How do you manage that?
Yeah. I make the time.
Could you repeat the question for everybody?
The question was, and this is the biggest challenge of everything I said here today probably, this may be the biggest challenge. How do we have time to cover all the material in a course? She was speaking specifically of a Calculus 3 course. How do we have time to cover the material and get the students up to the boards? And I'll say this, I just do it. And I know that's like, well, that's not helpful. But here's what I think. I try to orchestrate so that in the same amount of time I may have lectured something, I have my students engaged in some activity. Now, let me tell you this, I spend some time lecturing. There's a point in the class where I have to stop everything and I have to say some things or wrap some things up. Lilidol calls it leveling, where I have to stop and say, all these things just happened and I'm gonna level it so we're all theoretically in the same place. And so I just make decisions about what I'm going to have students get up to the boards and work on every day. And I'm going to make decisions about what things am I going to just lecture. But it is a daily occurrence that in my class, maybe it's 60-40, maybe it's 65-35 that my students are at the board on the higher end and I'm lecturing on the lesser amount. But it's a challenge. I would say to you, we can talk and like lay out the details, but I would just encourage you, if you're interested in this, just start trying it and see how you can navigate the coverage issue. Yeah.
so my question is about space. I don't have quite enough chalkboards in my classroom to get everyone to the board. I mean, short of doing some construction of my own, how can I do this?
Yeah. So I have some creative ideas and then a less creative idea. Creative ideas. There are products out on the market. There's like April purchased a big, basically it's a giant Post-it note that is made out of whiteboard type material. And so one of our classrooms, April blasted this gigantic piece of whiteboard Post-it note on the wall so we had more space. I've had other teachers go to Home Depot and purchase, it's like shower board, and they'll get it cut into certain size chunks and basically wallpaper their walls with this stuff. And that's a solution. There are, it's called Whiteboards. You can look it up, Google it. Whiteboards are these, almost like it comes in a poster board type pad, but they're whiteboard marker stuff. And then, if you can't go vertical, go horizontal. Get the horizontal whiteboards. And again, it's not like all the time, but as much as you can get your kids working together around the non-permanent surface, that would be sort of the less creative idea, is just get whiteboards and have them work in horizontal non-permanent surfaces. Yeah.
I couldn't help but notice that all the feedback was from the male students. How do the female students feel about this?
Yeah. That's a great question. And I had that thought. Let me tell you how this happened. I walked out of my class. The class ended. I said, hey, can I have some volunteers do this video? Because I'm walking to a workshop like literally right then. And those are the 4 that volunteered. So this was not a attempt to get anybody. But absolutely, I would love to be able to share with you what other students said. Some of the student quotes I had, of the student quotes, it was Madison and Tris were female, and then Miles was male. But no, absolutely, I appreciate that. And I will work to get some other voices in this as well. Yeah.
Okay, so, oh wow, this thing's loud. Okay, so I kind of had a double question. I'll try to make it as fast as possible. So firstly, like, if you've run out of space on the walls, could you perhaps, like, use, like, a whiteboard that's on wheels? Like, there's some at, like, the Marriott Library back at U of U, around where I live. Those are really handy. Like, could you slide them between the desks to add space?
Yeah.
Would that be feasible?
Absolutely. If that's available, absolutely. The idea, I didn't say this earlier, but another idea behind vertical non-permanent, getting students up on their feet adds an element of engagement. I don't know all the psychology behind it, but let me ask you all this. How many of you are the kind of people that when you have a phone call that you pace? There's something about being vertical and having those conversations or that thinking time that's good. So yes, if there's a way, a creative way that you can get students up and working, do it. Yes. Yes, sir.
Question. I was wondering what you think the cognitive difference is between having a professor talk about what a student might be doing on the whiteboard and having other students come up, because the end result is often a student who might have had the wrong answer is told or shown how to get the right answer. But how do you see the difference between students guiding this versus the professor doing it?
Yeah. So first of all, I'll say sometimes I do both. I mean, there's times where I make a decision about a particular topic or something I want to get across, and I'll make a decision that I'm going to say it, but then I'm going to have my students engage in some conversation about what I said. So I'm not, that would happen. But what's the difference between that and the other? Here's what I think it is. When student voices are getting to that place, there's this empowerment that the mathematics is something they can actually make sense of, that they can actually develop. It doesn't have to be that mathematics is something that I own and only I can give it to you. This is something that they can own and work on. So one of the ideas that I think happens in my classroom is this idea of reinvention. So for instance, let's go to my integer examples. A negative times a negative is a positive, right? And so we all know that. That's been invented or discovered, however you want to think about that. I want my students to reinvent that idea. So go to the board. We have tools, we have manipulatives, we have strategies. We start working, and a student will discover, reinvent in a moment. They'll say, hey, is it true that a negative times a negative is a positive? And I go, I don't know. How does that make sense? And we have a conversation. And when the class as a whole kind of feels like, yeah, a negative times a negative is a positive, man, that thing gets posted on the wall as that's, April's rule. A negative times a negative is a positive. And so I think the difference is they did it. They worked it. They figured it out. And that empowerment is an advantage in my mind than if I showed it to them first. Yeah.
I think we have time for one more question.
Okay.
What would you say to parents or administrators who say, this isn't the way I learn math, so you're not teaching math. Your kids aren't going to be prepared for tests or whatever. Yeah.
So I hear that. I've heard that a lot over the years, and I've been called to meet with parents over the years and have that conversation. And I usually start with something. Here's my favorite way to kind of get after that. Division of fractions. So first of all, parent, when was the last time you actually divided two fractions? outside of a math classroom. And here's what they say, oh, when I cook, when I'm baking. You see, if I want to take this recipe, but I don't want to make the full recipe, I want to take half of it. And I say, well, wait, what did you just do? You took the recipe and you cut it in half. You divided it by 2. That's not dividing by, say, a half. So even then I started thinking, like, okay, when did you ever divide by a half? They can't do it. Okay, how do you do it? Well, you keep the first fraction, you change it, and you flip the second fraction. Keep it, change it, flip it. Okay, why? I don't know. So we just work through an example like that, and I say, what we're trying to do for your children is have them, A, understand when it would ever be necessary to do this thing, say dividing fractions. B, how does it make sense? And it's hard. Division of fractions is a really hard one, but we have ways to make sense of it with manipulatives and other proportional reasoning thinking that division of fractions can make sense. And it takes some time. It's one of those, teaching is in a moment, but learning is over time. It takes some time, but in most cases, I get parents to be advocates for what's happening versus opponents. Once they understand, it's like knowledge is power. Once they understand what we're doing and why, we get advocates versus opponents. But it takes some time, takes some work.
Great. Let's thank Scott one more time.
Thank you.